All right, our first lesson of Unit 2 on quadratic functions just talks about how we're going to graph quadratic functions, some properties of quadratics, and then our transforming function form, and you'll see an example of that right here. So really our just most basic definition of a quadratic function is a function that can be written in the form one of two forms. We're going to focus on vertex form today, which is sometimes called our transformation form, and the second form would be standard form. Or you might see a factored form sometimes, but factored form comes from factoring down standard form, okay? If I'm going too fast because some of these notes are already written out, feel free to pause the video and copy them down, and then rejoin us when you are ready. So vertex form is what we're going to focus on today. Vertex form looks like this. F of x equals, and it's going to look pretty similar to what you've seen with absolute value functions. A, but now not times the absolute value, times x minus h squared. Remember, you always need some element of x squared for a quadratic function, plus k. And then for our standard form, f of x equals a x squared plus bx plus c, okay? And I'm actually going to move this down because I want to define a couple parts of that vertex form together. All right. So for vertex form, our a, h, and our k. This a value, vertical stretch or shrink, sometimes it's called a compression. Okay, it's a vertical stretch when the a value is greater than 1. It's a compression when it's less than 1. H is your shift left to right, and k is your shift up and down. All transformations you have seen before. You've seen these when we are graphing absolute value functions. We're going to continue to practice those today. Let's start with just graphing our parent function. The parent function is the most basic function in vertex form and standard. And let's start by making a table. Every time we introduce a new function, we'll start with an input-output table. Let's use some negative values, 0, and some positive values. And we're just plugging those in for x and squaring these. So negative 2 squared. And anytime you plug it in, you plug in a value, plug it in parentheses. So that negative 2, we're asking ourselves negative 2 times negative 2, so positive 4. Negative 1 times negative 1, 0, 1, and 4. And let's go graph these points. 4, negative 1, 1, 0, 0, positive 1, 1, and 2, 4. So similar but slightly different to your absolute value function. Looks like this. We're going to define a few characteristics of this graph off to the side. As you can see, this graph is U-shaped, and that U-shaped graph we call a parabola. All points are equidistant from, there's an axis of symmetry. This y-axis is our axis of symmetry. The axis of symmetry is a line where all the points are equidistant from that line. So all points are equidistant from the axis of symmetry. Okay, and because this is our parent function, our axis of symmetry is just so happens to be the y-axis, or the equation of the y-axis is x equals 0. As we graph some of these other functions, these quadratics, the axis of symmetry is going to move. It's not always going to be the y-axis. There's a vertex just like absolute value functions. The vertex is the highest or lowest point on the graph. The vertex will always be on the axis of symmetry, and in this case, the vertex is at the origin. It's at 0, 0. There will always be one y-intercept. There will sometimes be two, and our y-intercept here is also at the origin. There can be 2, 1, or 0 x-intercepts. You'll see examples of all of those shortly. There happens to be one x-intercept here. It's also at the origin. It's our parent function, so a lot of these are going to be similar. Domain. Domain is the x values that you can plug into this function. Okay, and you can plug in any x value. If you look, this function covers everything left to right. So our domain here would be all real numbers, or you could use this symbol, 2 L's with your R, and then your range. Your range represents the y values from a function, your outputs. And in this function, y equals x squared, the only outputs we're going to get here, because we're taking our inputs and squaring them, would be y values that are greater than or equal to 0. Right? There's nothing we can plug in that's going to give us a negative value because we're multiplying it by itself. So the range would be y is greater than or equal to 0. Okay, those are our most important properties and components of quadratic functions. Let's go graph some that are in vertex form. Okay, I'm going to show you a way to graph those. And something you might want to do, have these values handy, your parent function values, because we're just going to apply transformations to those. Okay, so let's do this first example together, and then I'll let you try number 2 on your own. For number 1, we're asked to graph the function and then identify the transformations. Let's identify the transformations first. Okay, this would be our left 3. Remember, it's always the opposite. This would be down 4. And then the 2, because it's greater than 1, is a vertical stretch by a factor of 2. So that graph, that parabola, is going to be more narrow. It's being pulled up and down. It's a vertical stretch by a factor of 2. It's going to be more of a narrow graph. Let's take those values and start with the same exact ones. However, our new vertex is going to be at -3, -4, because we shifted left 3 down 4. So now our starting point is going to be here. And then the only other change we need to account for is this vertical stretch by a factor of 2. And the way we account for that is our vertical stretch is our y values, so we just multiply all of these y values by 2. So now this new y value would be 8, 2, 2 times 0 is still 0, 2, and 8. And when you're graphing using transformations, just keep in mind that this input and this output, that's not -2, 8 from the origin. Instead, it's -2, 8 from your vertex. So we would go left 2 and then up 1, 2, 3, 4, 5, 6, 7, 8. So there's your -2, 8. Here's your -1, 2. +1, 2, and +2, 8. And there's our quadratic function. As you can see, it's been shifted left 3 down 4. Let's put a couple things on here. Let's identify a few things. Axis of symmetry would be at x equals -3. Remember, it's the vertical line going through the vertex. The vertex is at -3, -4. Our y-intercept, if we wanted to find our y-intercept, you could just plot one more point, because that would be 3 to the right of your vertex. And if we plugged in 3 to our parent function, 3 squared is 9. So we would have 9 here, but we would be multiplying that by 2 to get 18. So we would be going to the right 3 and up 18. Our y-intercept would actually be all the way up at 14. Remember, because we are 4 units down here. We were shifted down 4 units. Okay? Another way you could quickly get the y-intercept is just plug in 0 to your original equation. Our x-intercepts, we're not going to worry about those right now. They're not on easy points to find. I'll show you another time how we could find those x-intercepts. Let's put the domain in range. Domain, all real numbers. We can plug any x value in, and the range is everything above the y-coordinate of your vertex, which would be -4. So y is greater than or equal to -4. Okay, a lot of work there. Why don't you try the same for number 2? And then we will talk about some horizontal stretches and compressions. Go ahead and use your same parent function value of tables. I'm going to put that right here for you. Okay. And then don't forget to identify the transformations as well. Okay. All right, you can pause the video and work through number 2. This negative in front, it makes it open down. Another way we describe that is we say it's a reflection over the x-axis. Is another way to describe that parabola opening down. This -2 would be right 2. This +4 would be up 4. And then the only change we have to our parent function values would be all the y's are multiplied by a negative. They all become the opposite. So we get we now have a -4, -1, 0, -1, and -4. Just don't forget these points, the -2, -4, those come from our new vertex, which is at 2, 4, because we were shifted to the right 2 and up 4. And now we can go plot left 2 down 4, left 1 down 1, +1, -1, +2, -4. Remember, those points are from your vertex. And you would have something like this. Axis of symmetry would be at x equals 2. It's the x-coordinate of your vertex. The vertex was at +2, 4. Y-intercept is at 0, 0. Our x-intercepts, we have 2 of them here. You can see them. Our x-intercepts would be at 0, 0 as well, and +4, 0. Domain, all real numbers, and our range, everything less than or equal to 4. Everything below the y-coordinate of your vertex. All right, something I would like to talk about before we graph number 3 and 4. We'll graph 3 together and let you try 4 on your own, and then we'll do one more to finish up. You can sometimes have horizontal stretches and compressions. Okay, and the horizontal stretch or compression is going to be inside. So if we write out our vertex form, A times x minus h squared plus k, if there's a value in front of that x, which we call b, this value right here is going to act as your horizontal stretch or compression, okay? And a couple things to make note about this b value. If b is greater than 1, then it's going to be a horizontal compression. Okay, and a horizontal compression is going to look like a vertical stretch. It's going to squeeze together by a factor of the reciprocal, so 1 over b. If b is less than 1, but greater than 0, then this would be a horizontal stretch. It's going to open up wider. And we also say by the reciprocal. That's how we describe it. And then if we ever have negative values, if b is ever less than 0, then this is your reflection across the y-axis. And because parabolas are symmetrical, some of those reflections across the y-axis might be difficult to see, but we'll have an example of that down below here. All right, let's do the same thing we were doing up above, describing these transformations, starting with number 3. We'll do this one together. Okay, there's 2 transformations. Down 3. We're going to describe this together. This is this case right here, where b is a fraction that's less than 1, greater than 0. So we would say this is a horizontal we would say horizontal stretch by factor of 2. Okay. And I will show you what that looks like in your table. Let's practice starting with our table of values. Again, our parent function, -2, -1, 0, 1, and 2, 4, 1, 0, 1, and 4. I'll give you a chance to write those down. Remember, those are just our input-output values from our parent function. Our vertex. Our vertex is at 0, -3. There's no shift left to right at all, so we're going to start at 0, -3. And now, because this is a horizontal stretch, we're not going to multiply any of the y values from our parent function. We're going to multiply all the x values. And because it's 1/2, all of these x values, it's a horizontal stretch, they actually get multiplied by the reciprocal. You need to remember that you multiply by the reciprocal, which is why we describe it as a stretch of 2. So all the x values get multiplied by the reciprocal of 1/2. We get -4, -2, 0, 2, and 4. And remember, we graph these points. So -4, +4, not from the origin, but from our new, where our vertex is at. We're applying these transformations after we've shifted our quadratic function to the new starting point. So -4, +4 would be right here. -2, +1 right here. +2, +1, and 4, 4. As you can see, this graph is definitely wider than what we started with. Our vertex is at 0, -3. Our axis of symmetry is at x equals 0. It's our y-axis. And then domain, let's just finish with domain and range. We'll skip our intercepts for now. Domain, all real numbers. It's always going to be all real numbers for quadratics. You can plug in anything for x. And then your range, everything greater than your y-coordinate of your vertex. So y is greater than or equal to -3. Okay, why don't you try number 4 on your own, and then we will finish up on, we'll do number 5 together. Okay, we're going to skip 6 for now. So why don't you try number 4 on your own. I'll get you started with describing these 2 transformations. We'll describe these together, and then we'll put your parent function of values right here off to the side. -2, -1, 0, 1, and 2. That -6 is a shift to the right, 6. And now the 3, this is a whole number. So come back up top. When it's greater than 1, this is going to be a horizontal compression. It's going to squeeze that graph together. Horizontal compression by a factor of 1/3, always by the reciprocal. So you need to multiply all of the x coordinates by 1/3 and then go plot these values. And I actually just want to get you started with one thing here. Normally this would be a shift to the right 6 and we would be somewhere over here. But because this is a horizontal compression by a factor of 1/3, that vertex is not going to be shifted to the right 6. It's compressed by a factor of 1/3. So 6 times our 1/3 actually gives us a 2. So our starting point, our vertex, is going to be at positive 2, not 6. It's been compressed by a factor of 1/3, so we're going to start at 2. 2, 0 is your vertex. Why don't you get the rest of these points and plot them, and then list the axis of symmetry, vertex, domain, and range. Okay, hopefully you saw that your vertex was here at 0, 0, but it was shifted to the right 6, compressed by 1/3. We have negative 1/3, we have negative 2/3, 1/3, 2/3. Let's plot one more point. Normally this would give us 3, 9, and when we multiply the 3 by 1/3, this is going to give us a nice easy point. We get 1, 9. Therefore, negative 1, 9 would also be a point. So 1, 1, 2, 3, 4, 5, 6, 7, 8. We're all the way up here, running through my equation. That's all right. And somewhere over here, I'm okay with just 5 points total. So let's plot the negative 2/3 and positive 4. Negative 2/3 is about right here. Positive 4 would be right here. Do the same on the other side. You can hopefully see this graph is really tightly squeezed together because of this horizontal compression by a factor of 1/3. The vertex, let's do axis of sim. Your axis of symmetry is at x equals 2. It's this vertical line going through 2. Vertex is 2, 0. Domain, all real numbers. Range, y is everything greater than or equal to 0. Okay, let's try one more together, and then we will use a description to write a quadratic function in vertex form, and we'll finish there. Kind of a lot for notes because this is our first section for quadratic functions. They will get shorter throughout this unit. All right, let's do the same on number 5 where we're describing all the transformations. This would be down 1. This would be to the left 4. The 2, it's greater than 1. We just had an example when the b value is greater than 1. It's a horizontal compression by the reciprocal, so horizontal compression of 1/2, or by a factor of 1/2. And then this negative is going to make it reflect over the y. So this is kind of putting everything together. So normally our vertex would be at negative 4, negative 1. However, two things happen here. We're compressed by a factor of 1/2, so the x value, 4 times 1/2, is actually going to put our vertex at 2. So let's move this to 2, 1. Sorry, 2, negative 1. And then we're reflecting over the y-axis. So if we're 2 units away and we reflect to the other side, now our vertex would be over here at positive 2, negative 1. Because we reflected over the y-axis and we compressed by a factor of 1/2. Same parent function of values. Same table of values. And we just need to apply one transformation here. We need to multiply all of the x's by, remember the reciprocal, and don't forget to include the negative, negative 1/2. Negative 1/2, half, and negative 1/2. I'm going to scoot this over, so we're not going to do example number 4. Okay, so we get positive 1, positive 1/2, 0, negative 1/2, and negative 1. We are plotting these points, positive 1, positive 4, from our new vertex. So positive 1, positive 4 would be right here. You can plot the same on the other side. They're symmetrical. That's the negative 1, positive 4. And then half, 1, negative half, 1. There's our graph. Axis of symmetry would be at x equals 2. Vertex, positive 2, negative 1. And then our domain, all real numbers, range everything greater than or equal to -1. Okay, the last thing you might be asked to do is write the quadratic function given a description. So apply these transformations to our parent function. Apply a vertical compression by a factor of 1/3, 2 units to the right, 4 units down. Your function would look like this. Remember, vertical compression goes in front, so the 1/3. 2 units to the right. 2 units to the right means I need an x minus 2 in parentheses, and then 4 units down means I need a -4 at the end. Okay? Might have some like that on the homework tonight. All right, I apologize for the long, lengthy notes, but anytime we start a new unit, introduce a new function, they're going to be long. If that was confusing, please, you can see me for extra help. Try the homework tonight. We'll continue to practice in class this week.